Hello, and welcome to our Industry 4.0 educational series, sponsored by the Economic Growth Institute at the University of Michigan and the Manufacturing Growth Alliance. I am Stephanie Ludwig, a project manager here at the Institute, and I will be guiding you through the program today. EGI has been working with small to medium-sized manufacturers across the state of Michigan for more than 35 years, and we are thrilled to be here today partnering with MGA to assist in educating our manufacturers on the various core technologies of Industry 4.0. Today, our topic will be additive manufacturing, and we have Sean Hilbert from Cobra Aero to present. After the presentation, I will provide some additional information on current opportunities and resources available to manufacturers interested in implementing Industry 4.0 technologies who are located in Southwest Michigan, Northeast Michigan, and the Upper Peninsula. With that, I will pass it over to Sean.
Little background on this opening slide here. The Cobra Aero is in the unmanned propulsion space, and so a little different than the other two presentations. In that basically I'm going to give you a complete case study rather than we don't have a product necessarily for other companies unless they're very specifically in this market space. But we do a lot of really interesting things with additive manufacturing, and I want to kind of go through maybe a little bit of our journey on how we got there. The 3-cylinder engine that you see on the screen is something that several years ago the EGI helped us with in getting some what are called DMAP funds. We would have never been where we are today with this propulsion system if it weren't for the U of M Economic Growth Institute. So the EGI opened up a lot of doors for us over the years, and additive was one of those that kind of came along with the package. So go ahead to the next slide, please. So quick agenda, giving everybody the intro, kind of what is additive manufacturing. I think most people have a really good idea these days what additive manufacturing is, but maybe I'll have a couple other quick insights. How did we get involved? How do we utilize it? Kind of some benefits, some ROI. I mean, for the most part, unless you're buying simple desktop, almost toy kind of systems or hobby systems, the ROI can be a big deal. These are hundreds of thousands of dollars systems, and calculating an ROI is not easy. So I'll go through that a little bit. And then just a couple quick case studies. I've actually have our A33 engine and our A99 engine that I'll give a quick tour through. Okay, next slide. So who we are, just a little background on the company. We've actually have two companies under one roof. Cobra Moto has for almost 30 years now designed and developed and manufactured, distributed worldwide, some of the finest youth competition motorcycles anywhere. It's a very niche market. I call it a niche within a niche within a niche. But one of the things that we've done and have done over the years is, made some of the top performing small engines anywhere. And in about 2012, we decided to diversify into adjacent market spaces and take that propulsion technology into what was just a fledgling market at that time, and that is the UAS space, or unmanned aerial systems, essentially unmanned aircraft. Unmanned aircraft have grown into unmanned surface craft in the form of boats and things like that. Underwater craft, one of our bigger customers now, makes autonomous submarines. So we've kind of grown dramatically along with the marketplace on that side of the business. We've got customers including Textron and L3Harris. TerraDepth is the underwater startup that I just mentioned. Vayu actually is a company that's growing rapidly out of Ann Arbor that builds small aircraft. So it's fun to have customers all over the globe as well as very close to home. Okay, next slide. All right, so what is additive manufacturing? Like I said, I think most folks have a really good idea of what 3D printing or additive is. That terminology, kind of goes hand in hand, back and forth. There are lots of different technologies, though, to basically build up a part from some sort of base plate. There's extrusion deposition, which I think a lot of people are familiar with. Those are the way most of the hobby printers are architected these days. Powder or liquid bed. This is essentially where you have a scanning laser or other energy source to weld the material in a localized spot to the layer below, and you build these layers up one at a time. And then the latest technology, and we've got a very interesting technical agreement with Hewlett-Packard, and that is multi-jet fusion. And as you can kind of see in that picture there, it's not just a single point light source that is fusing the layer of material to the layer below. It's basically a sheet of light, and what that allows is you're starting to see a transition from use cases that are all about prototyping and sampling. All of a sudden, we're looking at ways of making additive parts very, very quickly, much less expensive, and we're starting to creep into that space of additive manufacturing being a very realistic and robust way to actually make high volume production parts. So what are some of the key tenets of additive? Obviously, it's adding versus subtracting. So adding material one little bit at a time versus, say, machining from a block of material. Digital versus analog. This is a little bit maybe difficult to wrap your head around, but think of it in terms of a casting or a forging. So you're going to create a net shape part or a near net shape part that you're then going to do further machining on. Well, in the analog world, you create a single use mold and you maybe pour that mold full of molten metal, and in the end you have your near net shape part. In the digital world, you have a platform that you can create any shape you want as long as it fits on that platform. And so digitally, you've got much more flexibility, you've got much more agility, you don't have tooling costs, the time to market and things like that is much, much quicker. It's also much more expensive from a piece cost standpoint. But as I mentioned, those costs are coming down every year. A good example of that is when I first joined Ford back in the early 90s, we bought our very first 3D printer, and it was $1 million machine. And nowadays you could buy a machine that did something very similar to that for your desktop, a really good one for your desktop, for about $1,000. So just like every other digital technology, there's an aggressive cost curve that's happening. And then the third thing, which is kind of an interesting paradox, is that complexity is helpful. Complexity is not helpful in any other manufacturing technology. So, if you have more detail on a machined part, for example, it gets more expensive. If you have more detail on a casting or a forging, those tools get more difficult and more expensive to make. And maybe the casting or the forging is more fragile. The process is less robust because you've got these details that you're trying to maintain over many, many parts. So next slide, I've got a couple of slides on the paradox because I think that's very important from an ROI standpoint. Here's just a picture I took offline. This is a bracket, and the part on the left is made with traditional manufacturing methods. So it's probably a piece of sheet metal that's maybe welded to a brace there. You've got your holes for mounting. And then the part on the right is additively made, something that would be incredibly hard to cast, very expensive to machine. But all those little webs and whatnot, there's two benefits there. The one benefit is that if you do this right, you're only putting material exactly where you need it. The other benefit is that those shapes are essentially self-supporting during the additive manufacturing process. So you don't have a lot of post work to take that part out of the additive machine and then put it into service. So you can see where, if you're using less and less material, that's less and less laser time, that's less time that you have to be, less touch time, so to speak, in the machine. All these things start adding up to a cost or or an ROI that starts to make more and more sense as you move forward in your additive journey, so to speak. Okay, next slide. Here's an actual case study from within Cobra. So we've got 3 what are called engine cylinders here. This is kind of the heart and soul of the small engines, or one of the small engines we produce for UAVs. And on the left, kind of in the back left corner there, is a cylinder that we used to make with traditional manufacturing means. In other words, those are 2 castings. So you've got the cylinder head, which is leaning against the cylinder, and that was created as a casting. And when we first jumped into metal additive manufacturing, we said, okay, listen, this is really cool. We can all of a sudden do things in our cylinder, on our cylinder, that we could never cast. So we're kind of grabbing more value out of the process. So if you look at that middle part, we did two major things here. One is that we integrated 2 parts into one. So we got rid of 6 fasteners. We got rid of some sealing interface surfaces where you could potentially have a failure mode. We lightweighted the part from getting those fasteners out. But then the other thing that's much more visible here is that we added a lot more cooling fins. In fact, we created those cooling fins that you could never cast. The spacing between the fins, the thickness of the fins are optimized for cooling that cylinder. But the only way we could make that part is through additive means. And then the next generation, which you see on the right and in the front, that's actually, if you look at the exhaust flange interface, which is that kind of oval interface at the bottom of the part with the 2 bolt holes. So you can see these are all the same part, although the part on the right takes everything one step further into the additive or design for additive realm. The cowling, which is on the outside of the cylinder, you can't see it on the other 2 parts, but that's integrated right into the print. And then rather than using fins, we're using a very small lattice structure. That's a flow through lattice that you see there. Highly complex part. It would be impossible to make from any other means. You couldn't cast that. You couldn't machine it. But the beauty is that when that part comes off the print bed, you don't have to do anything to it. There's no support structures to remove. So in other words, this is this paradox, this complexity paradox playing out to the full extreme. The part in the middle, I have a little inset down in the the left-hand corner there. That's that part kind of turned on its head as printed, and you see lots of support structure, right? To support all those fins during the printing process, we have to add all those in and then manually remove them and all that kind of thing. So by adding more complexity to the part, we've actually reduced costs and made it a lot more functional. Okay, next slide. All right, so some of the uses that we have within Cobra Aero, very traditional uses, R&D, rapid iteration of design. So by having machines in-house, we can literally turn ideas in a day and lots of rapid failures, so to speak, and turning things around, making the R&D process, the product development process, much more quick and just better, because we're able to do more iterations before we actually launch a product. Make like production as possible. And that's something that is maybe a little nuanced, but in the past, if we were making an engine case, the prototype might be machined from a piece of billet, and the production part might be a casting. And yeah, that's a subtle difference. There might be subtle differences in things like heat transfer coefficients and strength and whatnot, but those many times they don't make any difference in the end product. Sometimes they do. And so having a part exactly prototyped how you're going to go into production, we found very valuable. On the functional side of things, if you're going to truly embrace manufacturing, you're going to do things in the design process that are going to unlock a lot of value and that are going to make that business case much better. So, breaking feature constraints like spacing and wall thicknesses, and shapes and whatnot that you could never make in any other way. As I showed on that bracket, it allows structural optimization and lightweighting of a part. One of the interesting things about metal AM, is that the material properties exceed those of a casting, and that's mostly around porosity. So a typical casting might be 85% dense, where a typical printed metal part will be 98, 99% dense. So from a part to part variability standpoint, you're much better. And then incredible dimensional accuracy, just printing to a few microns. It's incredible. Operationally, ultra lean and clean. One of my favorite things when I give a tour in our facility is that I point out that our, and I put this in air quotes, our casting facility, or the place that we print metal, is 1 4-inch wall away from our lunchroom. You could never do that in the world of casting or forging. And then tooling. We do a lot of tooling that we print instead of make traditional means. And so a couple of quick case studies. Next slide. Here's some tooling. So on the left, you see a plastic printed part. This happens to be a hose cutting fixture that we printed very quickly. You can turn these things around and get them on the factory floor very quick. On the right is a little trickier. It's a conformally cooled injection mold insert. That the left-hand side of that picture is kind of the solid part. The right side is a see-through. You can see the water channels through the part. And think about that. Those are water channels that are printed right in place. You could never get water, cooling water, into some of those features and fingers and whatnot that you'd like to be able to cool to run parts much faster and run them more consistently. Okay, next slide. A couple of our engines. We have a lot of production parts that are printed, both with resins and thermoplastics, as well as metal. So cowlings and linkages, engine mounts, our exhaust system on our A33 engine on the left, the cylinders I already showed in a previous slide. So a large percentage of this engine is actually 3D printed right in our facility. The A99, which is a 3-cylinder version of this engine, intake manifold. We use powder bed fusion metal machine for all kinds of different parts, the cases, the exhaust, the cylinders. And one of the interesting things is, as I show on the bottom down there, printing the bill of materials. We have the cylinders and the cases on one build plate, and literally, it's a very lean approach. You get an order and print an engine. It's kind of it's not quite that easy, but you get the idea. It's very very agile. Okay, next slide. Some future work. This is the complexity paradox in neon lights, using highly complex shapes inside our exhaust system to attenuate sound. We're working with Wichita State University and some sound attenuation experts there to actually put that complexity paradox into full series production on exhaust systems, and actually using these meta materials, so to speak, to attenuate sound in new ways that have never been done in engine production before. Okay, next slide. And then finally, I'm just going to wrap up with the economics of AM and a couple of points here. The first one is it's very highly dependent on the type of business you're in. So if you're a job shop and you're doing this for other folks, then it's all about equipment utilization, right? It's all about that OEE that we heard about earlier, making sure that this very expensive asset stays productive for as many hours out of the day as possible. But in our case, it's a little bit different. We unlock a lot of the value by being able to design our own stuff and design it around the additive manufacturing process. So basically unlocking value in many different ways, value that the customer sees, value that we see by integrating parts and making things quicker and simpler and smoother. So it's a different ROI for our situation than it might be for somebody else's. And that's my second point there. If you control the design of your product, then the value proposition becomes much, much better. And then finally, this is something that we've kind of learned over time, and that is if you just kind of look at traditional accounting systems and say, okay, what's the ROI on this machine? How many parts are we making? How much does it, how much of the fixed cost needs to be amortized into each thing are we doing? I can guarantee you that you will have the wrong answer. And there's so many underestimations of what I call soft costs that you have to estimate through kind of probability functions. So, for example, if you're going to insource a part and do it additively versus outsource and have to deal with things like high MOQs and capital being tied up either locally or on the water, that's the things like supply chain variability and the low cost, the cost of lower agility. So for that, I mean, if your MOQ is 1,000 parts, and that's a low number for most companies in Michigan, but if your MOQ is 1,000 parts and you get 500 parts into that and realize, geez, I need to make a design change here. I need to throw away 500 parts. How do you estimate that in the cost of the part that you're trying to determine, whether to make additively or make through traditional means? And then the value of rapid iteration in the design process, being able to have a machine on site and rapidly iterate between one design iteration and the next has tremendous value. Okay, and next slide. That wraps it up. I'd be happy to link in with anybody on LinkedIn there. You can find me there. There's my email. If you have any questions about, hey, is this technology something that I should dive into? I'd be happy to answer any questions by phone, through LinkedIn, or by email.
So in order to support manufacturers statewide, there are several resources available. Next slide, please. One is through Automation Alley. Automation Alley is an Industry 4.0 knowledge center and means for business and cultures, and it's all about awareness. Their goal is helping companies understand what the Industry 4.0 shift means for businesses and culture and have a multitude of Industry 4.0 data and resources available to assist Michigan manufacturers. And through the state initiative, all manufacturers in the state will have access to these resources. They are currently offering Industry 4.0 leadership evaluations that will show companies how to use Industry 4.0 effectively to grow their business, and will be hosting Integrate in October, which is a global conference that includes keynote presentations, custom panel discussions, and also will have hands-on technology demonstrations. And through this initiative, all small manufacturers can get one free ticket to attend. So please reach out to Automation Alley for more information on that. In addition to the resources at Automation Alley, the Michigan Manufacturing Technology Center, or MMTC, is providing in-depth technology assessments for small to medium-sized manufacturers. They are recommending the Industry 4.0 technologies best suited for profitability improvement and job retention for each unique business. Additionally, they are providing the opportunities for companies to see the technologies firsthand through their roadshows. These are being scheduled across the entire state of Michigan, so please go to their website at the-center.org to find out when one will be in your region. Next slide. In addition to these statewide initiatives, there are also regional programming initiatives. These include providing regional webinars like today, and our goal is to continue to provide more educational content for companies as we move forward. So when you complete our survey that you'll receive this afternoon, please let us know if there are any specific topics you would like to see, or if you would like us to schedule something that digs in deeper to some of the technologies that you were introduced to today. And along with that educational component, we are also offering company assessments and technical assistance projects. Through these, MGA and EGI will work to ensure manufacturers in Southwest Michigan, Northeast Michigan, and the Upper Peninsula have the foundational and practical knowledge to move forward with implementing elements of Industry 4.0 to ensure they remain competitive in the years to come and to help meet that goal that Michigan has set to enter Industry 4.0 in all of our manufacturers. So with all of our history of running programs to support SMMs, what gets your attention most is when there is funding available to help you. So in our regional program, we will qualify a limited number of companies that have high potential projects for $10,000 in grant matching funds towards the implementation of an Industry 4.0 project. Now that you have learned about a few of the Industry 4.0 technologies from our presenters today, you might be wondering, how do I know if my company is ready to implement some of these technologies? Well, the next step for the MGA-EGI regional partnership is that if you are interested, EGI will conduct a top-down analysis of the company. So, of course, we'd have you sign a non-disclosure immediate agreement to ensure your company's data is protected and excluded from the Freedom of Information Act. And then we will conduct a detailed financial analysis of the company that will include a ratio analysis and company valuation. So if you have wondered what your company would be valued at, our analysis will not only help you better understand your company's value, but this analysis will allow us to see into your stability and strength and financial aptitude to handle and integrate some of these new technologies. So for companies that show they have that good financial stability and aptitude, EGI will then come to your facility and conduct an operational analysis to further evaluate other areas of business critical to tech integration, such as leadership, sales, planning, marketing, and use both the financial and operational analysis to determine some Industry 4.0 projects. All of this is done at no cost to you and with very minimal time commitment. So our output of these analyses is a level set recommendations to increase the firm's value and recommendation for those high leverage points of Industry 4.0 adoption that will be recommended as implementation projects that you can use that $10,000 on. Next slide. So to implement the high leverage point Industry 4.0 projects, our team will find the best resources for you to help implement this project. And then we will assist with the project management for its implementation along with your team. I would like to thank everyone for joining us today. If you have any questions about the topic presented, or you would like more information on the resources available, please feel free to reach out to me directly. You will find my contact information on the last slide of this video, and I'm happy to assist in any way I can. I hope you all have a great day, and thank you again.